Hello and welcome to this class on electron microscopy. This video is a shorter version of the class, so please, if possible, attend in person, okay? So first of all, what are we speaking about? Electron microscopes are devices that use an electron beam to focus on the surface of a sample using the nature, the wave, like the nature of electrons, and we can detect back the signal. So it works like a light microscope, a conventional light microscope, but instead of using a light beam, we are using a electron beam. There are mainly two kinds of electron microscope. One is called the scanning electron microscope. Focuses the beam on the surface and it scans the surface. So the beam, the focus of the microscope is moving across the surface of the sample. And we detect back the signal and we reconstruct the signal in our final image. This is the most common and the cheapest version of scanning electron microscopes available on the market. It's good for topography, it's good for morphology, it's good also for elemental composition. Second type of, second big category of electron microscope is the transmission electron microscope. Transmission electron microscope work in a different way because in this case, the electrons go through the surface of our samples, across all of the samples. The detector is on the opposite side. So only the electrons that can make it through the sample can be observed on the opposite side. And these electrons that traverse, that go across the sample, are the ones that generate the image. This is very good for the same things. We can observe some morphology, but also we can analyze the crystal structures, and we can even see individual atoms. But let's go back a little bit. Let's start from the optical microscope. These are devices that they use to observe a small specimen under visible light. They use optical lenses to focus and magnify the light, and they consist of many pieces that are common also with the scanning electron microscope and transmission electron microscope. So we will have a look also at the optical microscope. This is an example of optical microscope from 200 years ago. And they also work in either reflected and transmitted light, which is sort of similar to what happens with the scanning electron microscope and transmission electron microscope. What does this mean? For example, if the sample is transparent and thin, like cells, bacteria, living tissue, plants, etc., we can put a small slice of the sample on our microscope, and we can shine the light through the sample and observe the light that comes out of the opposite side. In a reflection microscope, we shine the light on the surface of the sample shines back some light, and we observe the light that comes back. But this is an old microscope from the 19th century. Nowadays, the light microscope look a lot more like the one on the right side, but more or less the pieces are the same. We have the lenses, we have the source of light. In the 19th microscope, it was a mirror, and a candle was used, or a light bulb, depending on the period of time. Then we have the eyepieces. And then we have something to regulate the distance between the lenses and the surface of the sample. This is because every lens only work at a specific distance with a very narrow depth of focus. So depending on the lens, lenses with lower magnifications can observe wider surfaces, more rough surfaces. Higher magnifications can only observe very flat surfaces usually. We say this is a modern optical microscope with everything. As I said before, this is the lenses that go directly in contact with almost in contact with your eyes, and they can have a small degree of magnification. They can also correct some problems with your eyes. For example, if your eyesight is not very good, these eyepieces can compensate. let's say, for example, that my left eye is weaker than my right eye, I can compensate the weakness of my eye in the eyepiece lens. Of course, there is a ring that's is used for the regulations. In modern microscope, we have cameras. So in the past, we have literally photo cameras. Nowadays, we have electric cameras that are connected to PCs. Then we have the magnification lenses. In this case, there is a revolver with 5 or 6 lenses, I think. Then there is a sample holder. They can have different shapes and different designs depending on what kind of samples we are using. There's the main structure, the arm that supports the microscope. Then we can regulate the focus using a dial. Usually there's 2 dials. One is more rough, so it moves the stage up and down faster. One is for precision, so it moves the stage up and down very small amounts, very slowly. So at the beginning, we go close enough to the surface of the sample using the rough dial, and then we use the more precise dial to optimize the distance between the lens and the surface of the sample. And there is a stage where is the sample holder. And in this case, we have a monitor as an output. It can be directly a monitor on the PC sometimes. Sometimes we have both. Probably in this design, we have both. It's both connected to a PC and has its own monitor. And in the past, well, not so far in the past, the stages could be moved by using 2 dials. Nowadays, many stages are electronic, so you can control it by your mouse and your PC. And then you can regulate the light intensity and other parameters, optical parameters, nowadays by electronics, in the past by using filters and add additional lenses, etc. Even nowadays there are solid filters that can be used, especially if you do things like fluorescence microscopy. You need to filter some lights. For example, you only need to shine, I don't know, red line at a specific wavelength to the sample, and you collect purple light, no, red light again, shifted red light probably, back. We need 2 filters, one going to the sample and one coming back from the sample. Green and blue also, red, green and blue are the most common, also yellow. Of course, the base, these things are very heavy because they need to be very stable. We not to move a lot, so then they cannot they need to be stable basically. That's why they are heavy, so the people don't move it by mistake, and they don't shake, because even small movements can ruin the images you are taking. And then there is the condenser that is basically to focus the light on the sample. And of course, we have the source of light. Then in this case, is it's in the back. And again, in the past, it used to be a candle or even the light of the sun, which was directed then to the microscope. Nowadays, we have fluorescent lamp, we have filament lamps, we have LED. Nowadays, probably LED is becoming the most common light source for microscopy. It didn't used to be. Well, and if we move from light microscope to electron microscope, we see that more or less the contents are the same. We have all parts of the microscope are in the left, and all the controls, more or less, so almost all the controls are on the right under the monitors. You can see there are additional dials, etc., joysticks and dials under the monitors. You can, for example, control the stages by using those joysticks. You have, of course, the monitors. Instead of having a lamp, you have a source of electrons. You have your lenses. Of course, you have inside of the chamber, because inside of this microscope, you need to have a vacuum in order to generate an electron beam. Inside of the chamber, in the vacuum, you have your sample holder. To focus, you use dials on the PC nowadays. And the camera is the detector for the electrons. In this case, is a secondary electron detector. And speaking of light sources, in the past we used to, in the optical microscope, we still use halogen lamps, tungsten lamp, fluorescent lamp, and LED lamps, with LED lamps becoming more and more common over time. While in electron microscope, we usually have only 3 types of sources. One is a tungsten filament. Tungsten filament is very close to what tungsten lamps are. In this case, we have a small wire of tungsten. Then we have lanthanum hexaboride. Lanthanum hexaboride is a crystal, is the pink crystal on the right. And the other possibility is usually to have a tungsten tip. So the resolution of a microscope is determined by the diameter of the electron spot on the sample. And apart from the diameter of the electron spot, we also need to have an electron density good enough to receive enough signal back to be able to read an image. This means that depending on the type of source, we can have different resolution. Tungsten filament, which is the cheapest solution, and also the solution that you need to change more often, because tungsten filaments break more often than the other sources. Works in a very simple way. You heat up the filament, and the filament emits electrons, while the other technologies are a little bit more complicated. Plus, there is also another effect which is called the Scott-Ray emission. The Scott-Ray emission extracts electrons through a combination of thermal energy and electric field, but we don't need to go in more detail. So in the tungsten filament is the most common. The tungsten filament needs to be changed after a few, like 40-50 hours of work. And the emission spot is a little bit wider, because you saw the shape of the filament, the sort of tip, the bent part of the filament, it's small, but it's not extremely small. The filament is heated up by a current, and the electrons are emitted mainly because of the thermal energy. The emitted electrons are then accelerated through the surface when they are used for the detection, etc., etc. I mean, the spot is small, and the electron density is quite high, but compared to the other technologies, the resolution of tungsten filament electron microscope is low. This is why this kind of electron microscope are getting a little less common, and they are used for benchtop electron microscope, not expensive electron microscope that you can use every day, and you can substitute the filament very easily. When we go to lanthanum hexaboride, the crystal emits the cathode of lanthanum hexaboride, is the electrons when it's heated at high temperature. And then again, just like the tungsten, these electrons are accelerated through the surface. This type of crystal is quite recent when compared to tungsten filaments. It has an excellent emission characteristics. It's very bright, so it makes very good high-resolution images, better than the tungsten filament. But of course, this kind of source is more expensive. And the last one is a tungsten crystal tip. And in this case, we are using a sharp tungsten crystal with a very narrow tip. The presence of a very narrow tip is good because it can create a very high density and very small electron beam, then allows us to get to higher resolutions and higher electron density, so brighter images. So if we just look at the schematics of light microscope and electron microscope, either scanning electron microscope or transmission electron microscope, the structure more or less is the same. You always have a source of something, which is either light or electrons. Then we have some lenses that are used to focus electron beam or light, and this can be optical lenses in the case of light, and electromagnetic lenses in the case of electron beams. Then for transmission, electron microscope, for transmission light microscope, you have the sample in the between. Not after the sample, you collect the light and you get the final image. For the secondary, for the scanning electron microscope, and for the reflection light microscope, the light is shined to the sample, and then the light that comes back as reflected is collected by another lens, and it goes to generate the image. So there are two types of light microscope, and there are two types of electron microscope, and they work in similar ways. One transmission light microscope is similar to the transmission electron microscope in structure and conceptually, and the scanning electron microscope is similar to the reflection light microscope. But there is another difference between the two microscopes. When we observe a sample with a light microscope, what we are really observing is the surface only. Electron beams carry a lot of energy, and this energy that the electron beams carry can allow the electron beams to penetrate inside the sample and to generate different types of electrons that we can detect, and even different types of X-rays and even cathodoluminescence. So we have different signals that come out of the sample once we shine our electron beam through the sample. We can collect, depending on the microscope and the detectors we use, we can collect specific type of information. We can obtain information about crystallography, composition, morphology, topography. So it's a versatile technique. One microscope with different detectors can obtain many types of different information. And I will just briefly speak about the main kinds. First type is Auger electrons. These electrons are very low energy, and they give information about elemental composition and the distribution of the sample. This is used in Auger electron spectroscopy, and it's good for surface chemistry, and we will talk a little bit more about Auger electron spectroscopy in the next class. The second type of electrons, a little deeper, they are the secondary electrons. They are still quite low energy electrons. They are generated when the primary electrons interact with the surface. These carry information about the topography. So the orientation of the surface changes the direction of these secondary electrons. So if we have a higher surface, this electrons shine in a specific direction and come back in another direction, hitting the detector. So we generate shadows and light in different portions of the sample. This is They are used mainly for imaging. Then we have the backscatter electrons. The backscattering electrons are a little bit higher energy and undergo scattering when they interact with the atoms in the specimen of the samples. They are deflected, redirected backwards at a specific angles, depending on the atomic composition. And by detecting and analyzing these backscattering electrons, we can obtain some information about the atomic arrangement, the material content, and elemental composition, and crystallography. So usually when we use backscatter electrons, what we do is we work on very smooth surfaces, because we want only the interaction between the electrons and the material to change the angles. In this way, when we detect the angles, the only source of deflection is the atoms in the structure, not the topography like in secondary electrons. In secondary electrons, we want to see topography of the samples, like we are making a map with the mountains and the hills and the lakes, etc. In backscattered electrons, we want to see the structure inside of the surface of the sample. So how the crystals are oriented and what materials the crystals are composed of. One next type of the mission is the characteristic X-rays. Characteristic X-rays are collected to a specific detector, and they give information about the atoms that are present inside of the material. They have specific energies that depends on the structure of the atoms. So depending on how heavy, how big the atom is, these electrons, these X-rays come back a specific energy. And this allows us to make a good mental analysis. So we collect the X-rays emitted, and we can say what are the elements that are present inside of the material. Not much about their crystal structure, etc., more about the energy. More about the composition. Sorry, not the energy. Then we have the cathodoluminescence, the continuous X-ray, sorry. The continuous X-rays are very produced by very high energy electrons, and they are quite deep. They come from quite deep inside the samples. They don't have a specific energy, so they don't form spikes of specific energies. They generate a continuum, and they give more information about electron density and atomic arrangement in the sample. Usually, these are considered to be a problem. Continuous electrons that are disturbing, are reducing our ability to measure other things. Okay? They are like a sort of noise. So there are not many detectors for continuous electrons that are used for specific scientific purposes. Then we have cathodoluminescence, even a little deeper than the continuous electrons. The sources are even a little deeper than continuous electrons. So this is a very special kind of detector, because we shine electrons to the samples and we collect back light. Cathodoluminescence is also used outside of electron microscopes. There are cathodoluminescence machines, but in the case of electron microscope, we can obtain information with a very local and very high resolution, up to the few nanometers. And this information is about the excitation state of the material. We can see the emission, the light emission, the spectra of the light emission of the samples, even in the visible or even in the ultraviolet. And this can be useful, for example, to measure stresses, because deformed crystal structures emit light which is shifted depending on how the structure is deformed. And it can be useful to detect defects in semiconductors and things like this. Everything that has important band gap information can be detected using cathode illuminations, basically. Not all materials generate a good cathode luminescence signal, of course. It depends on the band gap. Then we have the inelastic scattering. It's one of the techniques that is used to detect things on the opposite side of the sample, so in transmission conditions. This measures the energy loss of electrons when they interact on the sample, and so basically electrons go through the sample and they can interact with the atoms, losing energy. This is inelastic, because in a completely elastic scattering, the energy ongoing and coming back is the same. In inelastic, there is a loss of energy. Used to study the electronic structure, the elemental composition, chemical bonding inside of the sample. We can identify elements, quantify the concentration, etc. So it's another concentration and structure way of measurement technique. Then we have the incoherent elastic scattering. In this case, the electrons interact with the atoms and molecules without maintaining a specific relationship. Scattering electrons undergo change in direction, changes in energy, but they preserve the overall kinetic energy. Gives information about the atomic arrangement and the crystal lattice, etc. But it's quite a special technique. It's not so common to see incoherent elastic scattering detectors around. We can analyze the patterns, of course. Then we have finally the transmitted electrons. This is the portion of the electrons that go through the sample, more or less maintaining the same direction that they had when they enter. These are not scattered, these are not absorbed, and they pass through the sample without deviation. This is because, if you think about it, the nucleus of the atom is just very small, and there is a lot of empty space, so there is a relatively high chance that an electron can go through one atom without hitting the nucleus. Of course, then we have layers and layers of material, so we have many atoms, so the chances of going through without hitting anything decrease, and without getting deflected or absorbed, etc., decrease with the thickness of the sample. But in transmission electron microscope, we focus on the electrons that can make it to the opposite side. And finally, we have the elastic scattering. It refers to the scattering of electrons that can maintain their energy. They change direction, but they don't lose the energy. That's the point. They provide us again a structural technique, atomic layer arrangement, crystal lattice, etc. This is the design of the inside of a common scanning electron microscope. There are mainly two types of detector inside. One is the secondary electron detector, and one is the backscattered electron detector. So even if we spoke of many different types of probes, these two are the two detectors that are the most common inside a scanning electron microscope. And in the case of the secondary electron detector, what happens is it detects that the primary electrons go and hit the surface of the samples. At this point, secondary electrons are generated, and the secondary electrons go hit a detector, are reflected, and might go to a detector. And this is interesting because it depends on how the surface is oriented, how the electrons bounces back. The secondary electron is emitted back from the surface. It's not actually the primary that is bounced, but it's the secondary that is generated. And depending on the orientation, they might or might not hit the detector. This generates images that have a good three-dimensional look. That's why they are used for analyzing the surface of the samples. In the backscattered electrons, things work in a little different way, but scattered electrons are the same electrons that the surface that are bounced back. And these are used to analyze difference in composition, in particular in atomic number. Why? It depends on the size and, of course, of how heavy the element is. We will see it in a moment with an example, but before that, they play a role in elemental mapping. So they don't provide a composition, strictly speaking, a composition. They are used to give an image of different phases of the material. So heavier phases and lighter phases will look different in backscatter electrons. And this is because of this, basically. If we have a sample which is made of aluminum and copper, and we have two different regions, we will see that there's a higher chance for electrons to be backscattered when they hit copper with respect to when they hit aluminum. This is because of the size of the nucleus of copper is much bigger than the size of the nucleus of aluminum. So it's probability. There's a higher probability for an electron to be backscattered from copper than from aluminum. This is because, of course, the atomic number between copper and aluminum is different. Copper is like 29 and aluminum is 13. And so the effect is that the copper will look brighter, more white, because these images are always black and white. Copper will look much brighter, much whiter than aluminum in a backscattered image. And I give you an example here. In this case, we have a coating of chromium nitride on steel, and you can see there is on the top there is a black. On the left, we can see a sort of three-dimensional image. We can see like it's topography of the sample. On the right, the image looks more flat. This is because this left image is a secondary electron, and the detector is capturing only electrons that go in the direction of the detector, so it gives you a three-dimensional image as an output. Right is flat because it uses a backscattered electron detector, and in the right image, the intensity of color basically depends on the atomic number. That's why in the top region is resin, so it's mainly carbon. Carbon is light, and that's why it looks completely black. In the middle, we have a region which is chromium nitride. Chromium nitride is a little heavier, and so the average. Okay, chromium is heavy. Nitrogen is light. Chromium nitride is heavy but not so heavy. That's why it's a dark gray. And in the bottom region, there is a lighter gray area. This is steel. Steel has chromium, iron, nickel, etc. All these elements are very heavy, and that's why it looks more white. There are some black regions inside of the steel. These are large carbides. They are black because carbon, which is light, looks dark, like on the top, right? So we have in the left the topography, and in the right we have an idea of how heavy an element is. It gives you the distribution of elements, more or less, if we know what we are looking at. Another example is this one. These particles that look very beautiful are actually the effects on a coating. So these are crystals that are grown during a deposition process. On the left, we can see the image looks like a light microscope image, a photography. And you can see that the light seems to have a direction. So you see that the particles are whiter on the top left corner. This is because the detector of the secondary electrons is in the top left. And by this effect, you can see that it gives us a very three-dimensional idea of how round the particle is, how the shape of the particle is. You can also see the holes in the coating a little bit in the back. In the right image, we can see that these particles are heavy, that's why they are white. We lose the idea of depth, they look flat, but we have an idea which elements are heavier, which elements are lighter. The last example is this one. This is again a coating with a defect. You can see there are many defects on this surface actually, but the largest defect in the bottom is white in the backscattering image. The secondary electron image, we can see the topography. Looks like, again, it looks like pictures taken by a photo camera. On the right, we see that where there is that huge hole, we have a white signal. White signal means heavier elements. And the meaning and the explanation is very simple. The coating is lighter than the substrate. So this, only that defect is deep enough to reach the substrate. A few more considerations. One is about the working distance. As I mentioned before, working distance is the distance between the surface of the sample, the ideal distance between the surface of the sample and the lens, basically. And it's important to consider this, because the longer is the working distance, the wider is the area that we can keep in focus. So if we compare these four images, in the top left, you see that there is this spiral thing that is very clear in front, but there's another one in the back that looks really blurry. This is because we are using a working distance of 10 millimeters. So we are pretty close to the sample. If we reduce the working distance more, like for example 2 millimeters, probably only the top of the spiral would be in focus and the bottom would be completely out of focus. Then as we increase the working distance, so the sample goes farther away from the lens, we are able to see the spirals in the back. They get in focus. So when there is 41 millimeters, both the spiral on the top and the spiral on the back are more or less in focus. This is because the closer we get to the lenses, the wider the angles. So the focus, the area that can be in focus. Another way to control the areas that are in focus is by the aperture of the lenses. So if the aperture is very small, only a small amount of light can penetrate, but we are able to focus deeper region. That's why with the 100 microns aperture, we can keep in focus all of the spiral. If we use a larger aperture, we can collect much more light back. So it's easier to make an image, but the image will be out of focus. So let me repeat this again. Small apertures means that we collect very little light, so the images are darker, but more in focus because we can focus larger areas, deeper areas. With wider apertures, we can collect a lot of light, but images will look more blurry because the deep of field, so how much area we can focus, is decreased. So just a few images from my database. These are images obtained with a secondary electron detector on titanium particles. You can see that the light seems to be shining through the top left. This is because the secondary electron is in the top left. This is a double coating. On the bottom there is a coating which is about 1 micron thick, which is of silver, and on the top you can see there is another coating, but this is a cross section, so the coating is broken, right? On the top there is another layer, that layer is about 100 nanometer, so it's extremely thin. Even if it's extremely thin, you see it's very good. There is no defects in the surface. There are some sort of bubbles, but that is not a defect because they're not broken. It's because of the shape of the substrate. And if you look even a little more, if you focus a little bit more on the small coatings, the one that I told you is about 100 nanometers, you will see that there are two layers, one a little darker, one only a little lighter. This is because this special coating is about 45 nanometers of titanium oxide and 45 nanometers, sorry, the first layer is aluminum oxide and the second layer is titanium oxide. And this is used for corrosion protection. It's extremely powerful, extremely thin. It's probably the tiniest coating that can be used for corrosion protection. This is a structure made of tantalum, observed again in secondary electrons, and this is used to simulate human bone. So human bone can attach to this structure and grow because they look like they have a structure which is similar to that of human bones. It is used in prosthetic materials. These are nice small crystals of salt. They are deposited around some defects. So this is again a coating seen from the top. There are some holes, as you can see, and around these holes, these depositions occur at specific diameters, specific distances. Again, this is another coating, it's a very special one. This is observed in backscatter electrons, so you can see differences in atomic number. If you see, this is a cross section, so it's cut. But if you look carefully, you see that there's actually hundreds of smaller coatings. So the total thickness of this coating is about, if I don't remember, I think 150 microns, something like that. But it's made of many layers of electrodeposited nickel. This is another typical application of electron microscopy, scanning electron microscopy in particular. This is a piece of steel that has been broken, and the scanning electron microscopy is used to look at the surface, to search the defect, and to observe the morphology, so how it broke down. This is another typical application. We used some special filter to capture particles in the air, and we observe those particles using scanning electron microscope. In this image you see the filter, which is the fluffy substance. You see some fibers. Those fibers are asbestos fibers, so they are extremely dangerous, and they were captured in an industrial area. It means there is there is asbesto in the air of this industrial area. So this is everything for the video. Next step, you need to go to Moodle and do the homework. The homework is quite easy. It's an image. You need to find some information about the image. It's extremely easy, so don't worry too much. If you need any help, you can watch again this presentation, because during this video presentation I showed you all the information that is requested by the test. Okay, see you.